Good morning, everybody. Now we are on chapter 6. I would like to start today's talk on this control flow. And we actually are starting the Unit 2 programming language features. And this session, I will try to be lighter because the previous 2-3 weeks, we have been very heavy on a lot of homework and a lot of things to do, because as I mentioned, the chapters 2, 3, 4, the week 2, 3, and 4, we will be very heavy. After that, we are lighter, much lighter actually, compared to the week 2, 3, 4, because the week 2, 3, 4, we are strongly involved in the compiler design issue and the language design issues. Starting from this session, we are out of the front end, back end of the compiler. So right now we are more focused on the language features. The language features will not involve not many implementation issue. So basically we'll be just discussing the a few features of the languages. So starting from here, we actually are comparing and discussing different design of the languages. So let's get started. We are on chapter 6, control flow. First, I'd like to talk about the sequential programming or unstructured programming. When computer just get started, the first programming language is actually sequential programming. It is similar to assembly language. It just performs statement by statement, statement by statement, and then if there is some jump or branch statement, you will go to certain code section, get executed, and then being jump back, and then jump back to the current flow. That is the sequential programming. And how about the era before sequential programming? At that time, we call it as hardwired design. Hardwired design means that you have a finite state machine. You use transistor, you use certain logic gates, and then you try to perform some logic function, but actually not really programmable. And that is called hardwired design. You can think about it as just soldering some transistor on the PC board, and that is the day before programming. And then later, when high-level language gets started and assembly language gets started, they are all sequential programming. That is executing the statement one by one. And then these languages start to become very massive when the program get bigger. In the early day, every program is very small, and then you basically need to read in your program not by the disk or any tape or anything. At the very beginning, the input of the program is actually a deck of cards. So at that time, we have the input deck, we have the output deck, we have the program deck, something like that. And after a while, we started to have the floppy disk and hard disk, and we started to use tape for input and backup. And program get bigger, and it is hard to use this sequential programming. So we start to have this structured programming. And at that time, actually the first structured programming is probably PL0 or PL1, and then go to Pascal language. And here it then started to have this sequential programming. In sequential programming, they are still have this sequencing, that's sequential programming, and you have selection and loop. You have conditions, and also you have the repetition. and then you also have the start to have functional procedure. And functional procedure can be considered as another kind of the branching or special kind of branching or special kind of selection. And for the program stay in single thread, single processor for quite a while, maybe from 1970 to late 1980 or even 1990s. Then we start to see the multi-thread, multi-process system start to happen, start to show up. And at that time, we start to have some need for Windows programming. And then later, we start to have a need for networking programming and multi-processor programming. So language turned to object-oriented programming starting from maybe 1985 to 1990. At that time, object-oriented programming still in single thread, but later, because of the Windows need, then start to have multi-threading, but in single processor environment. And later, we start to see the need for program in the client-server model in the network environment. And we start to see the multi-processing, multi-core. We start to see the event loop, event-driven programming. And all of these can be called some sort of concurrent programming. But concurrent programming doesn't mean it is actually multi-processing, that you have multiple processes to support a program. It actually at least need to have the multi-threading. That means that your program doesn't follow a single flow, but multiple flow. And object-oriented programming can be single thread or multi-thread, and that depends on how you set up the environment and also your program's own nature. But in concurrent programming, we would keep hearing these terms: object-oriented programming, event loop programming, event-driven programming, multi-threading, multi-processing. They all carry certain meaning. Object-oriented programming was adopted because of the Windows system. You need to have window object, you need to have widget, you need to have form, those kind of things. And then event loop programming is for JavaScript and used in a single thread environment, but try to mimic the feature of multi-threading. So you have a loop and have several events sent to the single threaded loop to handle it. But from the user's point of view, it looks like it's multi-threading, but in fact, it's only a single thread handling the event queue. And then event queue got expanded, and they might, in certain system, to have multiple threads to support it, it becomes event-driven programming. And event-driven programming later been generalized or take advantage of the multi-threading feature, start to have these different packages or the APIs to support Java and different language. And we start to hear multi-threading, multi-processing, and even multi-programming MPI interfaces. So overall, these are the advances for the control flow for our programs. And in our textbook, we have different topics for control flow. So here are we will get started from the basic paradigm for control flow. For Goto, branch, jump, and sequencing. That's the first when assembly language gets started. And we also have topic on selection, iteration, procedural abstraction, and recursion. Up to here are called structural programming. And then we have concurrency, that is actually multi-threading handling, and we have exception handling and speculation. And we also have non-determinacy. These are more advanced topics. We will talk about the concurrency in chapter 13. And I believe we handle this exception handling in chapter 9, the procedures. And non-determinacy actually talk about random or some different type of control that is not actually deterministic. So let's look at the unstructured control flow. This basically used more for assembly language, COBOL, Fortran, these early languages. We have sequencing, that for sure, statement by statement, and early language like COBOL or BASIC. They even have either line number or section number, those kind of numbers to help doing sequencing. And help the go-to statement with those segment or labels. So we have go-to statement, branch, jump, and we also have co-segment or segment COBOL. Unstructured control flow. Unstructured control flow, the use of go-to statements and the statement labels to implement control flow. Generally considered bad. But why people use it? Because it is cheaper. You just need to have some branch, and then you will just need a program counter, and then branch. You don't need to pay a lot of hardware penalty on switching of the control flow. Most can be replaced by structured with some exception. Break from a nested loop. This one actually is an exception. Return from multiple routine calls. These two, but nowadays we consider the break and the return as one break level for a procedure. I'll talk about this later. Java has no go-to statement. In fact, it has the go-to statement, but now it is not really supported, or it actually doesn't have the meaning anymore. Language feature to support unstructured control flow can include sequencing, branching on condition, and go-to labels. Sequencing, the executions of statements and evaluation of expression is usually in the order in which they appear in a program text. Sequencing specifies a linear ordering of statements, one statement follows another, very imperative manual-type operation. These are very simple. A compound statement is a delimited list of statements. So this talk about the block. And in different language, you have different way of doing to construct a block. In C++, Java, we do see these braces and left braces and right braces, and some people call this curl bracket or right curl bracket. It's okay, but actually this left right bracket curly bracket actually is the most popular begin and end right now for the block for modern languages, because it is much more simple. And Pascal modular use begin end. Ada use declare begin end. And these are the compound statements or code blocks. Now let's look at the jump and the C++ Goto. On the left hand side, you see the assembly jump. On the right hand side, you see on the right hand side, you see the C++ Goto. And basically, let's look at this C++ Goto first. So if integer, we declare an integer x equals 3, and then we go to quit it. And you would go to here, and you actually have no way of doing this x equals 999. And you jump to here, and then you return x. So x equals 3 got returned. On the left-hand side, you actually move the 3 to register EAX, and then jump to the label here. So you go to here, and this is not executed, and then you return. You return with the x value in the register. So you would have to read register to get the value of the X. Assembly, branch, and jump. Okay, right here you have so many different instruction in the assembly code, and I believe in every language, in every assembly language, jump or branch are a big collection of the instructions. So here are the basic one. You have jump, always jump. So you see a jump statement that is automatic jump. There's no condition to check. Then jump greater than, jump greater than, jump greater equal. This A probably is called above or something, but it is for unsigned. That's why you call above or below, because this is actually usually used for the alphabetical order. So you have jump above or equal, and jump below equal, and jump on condition or unsigned overflow or multi-precision add, and jump compare the register with 0, and jump equal, jump greater than equal, jump less than, jump less equal, jump non-equal, jump on overflow. These are different typical. These are typical jump operands. And some one with the condition, we call it conditional jump. And conditional jump, usually you have to check the program status register to know that whether you will have jump or not. So right here, let's look at this example, how to use compare and jump if equal. So we move 3 to this register, compare with 3. So actually, it is comparing these two numbers, and then you will set the flag. So if the flag say it's equal, then we jump to here, and apparently we will jump, and then this is not executed. And there is another thing that right here we have another example using the jump if less than. So we move 1 to this register, and then compare the register with 3 if less than. Based on that, will be checking this compare will set the flag in the program status register. So we look at the flag, and if it is less than, then we jump to here and then return. Now let's look at the COBOL. COBOL is high-level language, so it's different from the assembly code. The way COBOL do it is COBOL has a program of such structure. So if you look at the program such structure, you will know that this COBOL program is just like a book. You have program division. Division is bigger than section. Section bigger than paragraph. Paragraph bigger than sentence. Sentence bigger than statement. So that's how COBOL being structured. And actually, this is just like natural language when you write some article. And I believe that is the early days of perception that high-level language need to be similar to English. That is how people get started from programming language. And COBOL is short for, the name of COBOL is actually Common Business Oriented Language. So that's a language used for business use. And I just read a report that even today, 60 years after the invention of the COBOL language, there are still a lot of company or bank using the COBOL language, but there is no programmer to maintain it. And there are certain qualified engineer that can still maintain the program. They are all at the ages of 75, 72, those kind of age. And no young people would actually be able to and also interested in learning COBOL anymore to support it. And COBOL's section look like this. You have 000, this is the section name. You have main, and then 300 for housekeeping, 500 for machine processing, and then you divide it into 530 re-inventory, 550 insert data, 555 insert database, 700 cleanup. So you use the 100 digit for larger module, and inside 500 you have 530 and 550. Inside 550 you have 555. So use 3-digit code to classify or actually line up your code into different sections. So the COBOL language will look like this. You have the comment, and actually at that time we have this text-only environment. And as I mentioned, that early day terminal, when we see the deep binding example in, actually that would be the chapter, deep binding is in chapter 3 in week 3 session 1. That's in chapter 3. Actually, I told you, you guys that the early day, the terminal is 80 character a line, and then there is about 24 line or something. That's the screen that we see. Actually, I saw this before when I was just a college student. That we do programming like this in 1980 something. I have been doing a lot of this kind of program before, and even this colored monitor, I believe, is late 80s. The early 80s, we only have monochrome monitor. Or some poor student like me, I don't have the access to the colored monitor. We only have the single color. Starting from green color, and then later has the white, had the orange, different color for the monitor. But at the beginning, we all see a lot of the green monitors. And here we have 000 for the section main and procedure division. And then here is a entry label using inventory PCB mask. Move this to this, perform 800. So you will move this and then to this as a section label or something, and then perform 800. So it will jump to 800, call 800 to execute, and then after that, you actually perform 300 bookkeeping, and until it meet this 300 bookkeeping, housekeeping exit, then you return, and then you perform 500 until you return, and then something like that. So this is the main program. You just follow the flow. You jump to certain section and come back. Jump to certain section and come back. And at the end, you have 999. Go back. Okay. Now let's look at the lecture 2. Expression evaluation, continue and exit condition. So now we are at we finish the sequencing and branching. Let's look at selection, iteration, procedural, abstraction, and recursion. We start to look at the structure of the program now. So before we go to the structure program, let's look at the expression evaluation, because condition, branch condition, or the if condition or while condition is commonly used in this structured program. So there are a lot of the true or false to be decided, and that is the expression evaluation. And right here, we talk about this expression evaluation first. And for expression evaluation, it has the infix, prefix, postfix operations. And in the early day, we had a prefix operator and postfix calculator or programs. but now it's all infix. And for infix, postfix, and prefix is something like this. For example, we have the parenthesis a times b plus c divided by d. This is our regular expression. And if it is written in postfix, it will be something like this: ab times parenthesis cd divided another parenthesis. So this is operand. This is the expression 1, expression 2, and then plus. So you always put the operator at the end of a expression. And then prefix is different, is opposite. You put the operator at front. So you have the time AB divided CD and then plus this expression 1 and expression 2. And the precedence and associativity actually will determine which part will be evaluated first. So we will have figure 6.1. C language have 15 level. It's way too many to remember. And actually Java have fewer, but not too much fewer. And Pascal only have 3 levels. A 3 level is too few to have good semantics. And Fortran has 8, Ada has 6. So all the language are in between C and the Pascal. But when you are not sure, then you just use parentheses to help. So right here, figure 6.1 is a comparison for the different schemes. And I believe that Java is closer to C, also have many levels. It said that Java don't have this, probably has it, but not frequently used for the left shift and right shift of it. Oh, probably not. No, none of this. But Java do have the bitwise inclusive or bitwise or bitwise and. Java do have this, but not the shift part. And now notice the shift assignment as well. So C would be a typical precedence that we can study. The post-increment, post-decrement has the highest priority. And then is pre-increment, pre-decrement, that is a second level, and unary plus minus sign. And then, okay, and then division and multiplication and modulo, and then plus minus sign. And then assignment, actually the equality check and logical operation are in this region. And assignment probably is the lowest, almost like lowest. Okay, and Ada has 6. And Pascal only have not, actually it's 4 level. It has the division, plus minus, and also greater comparison, 3 type. And it's not probably only for logic. And right here is for Fortran. Differentiation is evaluation. Auto operand evaluation, general ordering of the operand evaluation, generally none. Application of arithmetic identity, distinguish between commutative, commutative, commutativity, and assumed to be safe, associativity. And actually, this is just mathematical meaning. And this one is actually, okay, this tells you that this statement will work if A not equal to maximum integer and B not equal to minimum integer and C less than 0. This actually means that even though you have the expression, but sometimes it still doesn't work, because if your number is actually out of the domain for the expression, then it may or may not work. So if you actually provide parentheses, the parentheses will be operated first. But sometimes if the sum already create the overflow or underflow, then you will not be able to operate. And for parentheses, there is inviolability of the parentheses. Usually, parentheses will be taking higher order of consideration. Expression evaluation, we consider this. If A greater equal to B, there is no point evaluating B less than C, because A already less than this already be false. This is called short-circuiting. Short-circuiting means if the first part of the logic is true or false, that cause the whole statement be true or false, then you don't need to evaluate the second part. For example, in AND's case, if the first part is false, then there is no need to evaluate the second part. That doesn't need to be evaluated at all. And if there is an OR, and then, for example, this statement, if F is true, then the message will not be actually evaluated. These are called short-circuiting. And right here, this one, a pointer P, if it is 0, say, 0 means null. So there is no such, the pointer doesn't point to anything. And in this case, pointer pointing to full function actually will not be evaluated. And this actually is the pointer as logic. In C language, a null actually equal to 0, and it's also considered as false. So this one is also to evaluate a pointer as logic. And then if it is a pointer point to something, then we evaluate the second part. If it is not, then we don't need to evaluate the second part. So this is in C language. And this one, if B not equal to 0, then we evaluate this. If B equals to 0, then the first part is false. Then this division by 0, we don't want it to be evaluated. So these are how people use, especially in C language, for short-circuiting, and cannot be avoided to allow for side effects in condition functions. If expression evaluation, variable as values and versus variable as references. And that is the reference model. This is similar to the call by value, call by reference argument, but here is the evaluation of the expression. And we know I mentioned before that expression sometimes, like a plus sign, minus sign, it is actually similar to function call. So you can also have this argument for value, available as value, or available as reference argument, because it's just like a function call. But anyway, the popular C, Pascal, Ada, they all are value-oriented language, and reference-oriented language actually are not a popular or majority or mainstream one. So most functional languages like Lisp, Scheme, ML, Clue, Smalltalk, these are more reference-oriented language. Argo 68 is kind of halfway in between. Java deliberately in between. They have built-in type value, user-defined type object reference, because Java has a primitive data type that will use value, and the user-defined object actually using the reference. So, for example, I compare one strings and the other string using the double equal sign, then that will be comparing the hash code or the ages or the reference of the string object instead of comparing the content. But if you want to compare the content, you use that equal. So Java has the reference-oriented feature, but not in C or Pascal or Ada. So right here, if I have A, B, C, 4 to 2, then this is value-oriented. And if I have the integer object, and then A is pointing to 4, B, C are referencing the same object too, and some of the constant in the Java or language, actually, they are referencing the immutable data. Some language use that. So in that case, that is referencing the same object and will have the same reference value. When you compare using the double equal sign, that may comparing the ages instead of the value in the content. If they pointing to the same object, then they will be equal. If not, even the content is the same, still be false. So expression evaluation, in the reference model, we have the boxing, unboxing issue as well. So from primitive to regular class, it's called auto boxing, and the opposite direction is called unboxing. And why we bring this up is because in the Java language or C# language, they have the auto boxing, auto unboxing. So when they are compare, say, two integer object of the wrapper class, they try to use the double equal sign to compare, or you compare an integer to a wrapper class, it actually will be related to the boxing, unboxing situation. So actually, you need to take care of it. It's not really 100% value model or reference model, especially for these wrapper classes. Expression evaluation, expression-oriented versus statement-oriented language. And expression-oriented language are more functional language, Lisp, Scheme, ML, and Argo 68. Statement-oriented are most imperative languages. So basically still functional language versus imperative languages. C is kind of halfway in between, allow expression to appear instead of statements. So this expression evaluation is whether it's expression oriented or statement oriented. It basically based on after the evaluation whether you return some value true or false, or you actually set in some variable or by the statement. That actually is how you look at whether it's expression oriented or statement oriented. So basically, it's like, do you return some true or false, or do you set some flag, something like that. That's the main difference between these two evaluation methods. Okay, let me check. We are on the lecture 3. Let me check if anybody around. Okay, we have. Let me check who is around. Oh, Miguel is around. Let's say hello to him. Okay, I'll return to the lecture. I got some little break here. Then the next one is orthogonality. And what is orthogonality? That is feature that can be used in any combination. Actually, that is what. It's hard to understand this word orthogonality from its definition. You can check the dictionary, but it's not a definition for a term in computer. So the orthogonality meaning is consistent. Actually, it means consistent. And even this word consistent is not easy to understand it. What I should say is actually orthogonality means if it is an apple, you call it an apple. If it is a chicken, you call it a chicken. And if it is a coin, you use it wherever coins are accepted. And that is actually, if it is an expression, you would be able to put it in anywhere expression can be put. If the language has such a feature, we call it has the orthogonality. That means, okay, let's look at the Ogo 68 situation. We have A assigned by this, right? This is actually a statement. So it assigned by a statement, but this statement is what? It's actually, let's look at the previous slides. Now this one. Let me try another one. Okay, this is not this one. This one is expression oriented, or actually is statement oriented, right? So Ogo 68 is expression oriented. So you will return the true false for the statement. And right here, this Ogo 68, this whole statement has the expression feature. So it actually will return something. It will return something. So A is assigned by if B less than C, then D. So D will be returned for this whole statement if B is less than C. Otherwise, we will return E. So actually, this statement is equal to the Java statement that we have parentheses B less than C, and then D question mark D, and then column E, the same as the conditional statement. And so this actually will return something. And since it returns certain, say, integer or certain value, that actually can be assigned to A. So that is the feature of the orthogonality. When there is something that will return an integer, it is considered the whole thing is an integer. You just put this whole statement in everywhere that the integer is accepted. So let's assign, if B less than C, we assign D to A. And then B equals begin and end of this. So this actually is, for example, if it is accept the return value with this the last assignment, even though it's a function call, but it will evaluate, for example, the last one will be assigned to this. And that is the return value of this COBOL. So this is accepted. And then G of the D, G with the parameter D, this G can be a function, then this is one statement, and 2 plus 3 is the statement. So the orthogonality actually means if a statement or if a expression has certain return value, then that can be put anywhere that is that a expression or a statement is accepted for the integer. Then the whole block can be ported anywhere as an orthogonality. But not every language will implement this. because it will make the language very busy. So in C language, if A equals B, then we do something. If A assigned by B, then we do something. But A assigned by B actually will be returning B value. So B value will be evaluated for this condition. So if B is 0, say, then if B 0 is considered false in logic for C language. So if A assigned by B is 0, then A and B both are 0, and this value actually returns a 0 over here. But assignment still accepted as a logic value, and then this is called orthogonality. So anywhere that they accept a logic, we still can use A equals B, A assigned by B, and that is orthogonality. But in Java language, say, we put A assigned by B, the return value is actually a integer 0, and it will not be accepted as a boolean value. But if this is put somewhere else, say in Java language, I have the A assigned by B, the return value is B value, but this value can be further assigned to C. Then in that situation, Java probably accept it. And that is the feature of orthogonality. So different language has different implementation to enforce this orthogonality. And I don't think that there is a language take 100% orthogonality. Otherwise, that language will be very messy, very hard to read. And let's look at here. Since this is acceptable as a value for integer, this stem statement can be accepted as a Boolean value for August 68. So right here, if we have B not equals 0, then B divided by B equals C, then we will return this value. And then else we return this false. And since both of these will return the Boolean value, so the whole statement right here can be used as a Boolean value. And similarly here, if F, then we return true. Otherwise, we return messy. Both true and messy are considered Boolean value. So this whole statement can be put wherever Boolean value is accepted. That's we call it orthogonality. Expression evaluation, special cases, combination assignment operator. Here, actually, we are talking about a side effects. Some side effect will be used. So we have this A equals A plus 1. Then we can have this A plus equals 1. A plus equals 1 is equivalent to this. That's a special case. And right here we have B dot C indexed by 3 dot D. This will be equal to this times this. And this will be equivalent to this statement. And actually, this is a B object's data field, this data field D. Sorry, I just mute the phone call. Let me just mute it. Okay, so whenever something can be used as a variable, you will treat it just like a normal variable. So this whole thing can be treated as a variable, so it can be time equals assigned by multiplied by E and then assigned to itself. So the side effect of a function as parameter here is a assignment as a parameter. Let's look at this right-hand side first. This function will return a integer value, and that integer value is used as an index for a, and then this a with that index will be increased by 1, so that this one is safe. And this post and pre-increment or decrement, actually you get the index value, and then you actually has the post increment and or pre-increment. These are both okay. So as long as your value is put in what it is accepted, the orthogonality may have some side effect, but sometimes it is actually safe. So this multi-way assignment through same thing, it will be safe. But let's look at this one. We have this function, and then here we have a function as a pointer being passed here. So index fn is a function pointer. It's a function with integer as parameter, integer n as parameter, and that pointer being passed as a value in the C language as a function call. So right here, this one can be any function that people put in here. So we go through here. So the J value actually depending on this index function. So different index function will get different way of calculating the J value, and we will get different J value. And here we cannot simply write orthogonality because this function is changing. So it doesn't bind to the same function. So this statement actually is not safe. It is violating the orthogonality violation because the value we never know whether it's return a boolean or it return the index value or index what, because the function can always be passed with different value. It may be out of bound. It may be another problem was created by this. It's violating the orthogonality. So this one is equivalent to this, and then this one actually equivalent to this, and both are safe. And the next one is initialization. Pascal language has no initialization facility. You can only use a sign. Some language has the initialization, and some language implement partial initialization. Say if we have the Java language, and Java language have private data field, and that's assigned as an instance variable. So those instance variable, once you create an object, a implicit constructor will be called, and those variable will be initiated. But if you define a variable in say a function or method function in say the public static void main, the main function, it defines some integer in that function instead of having it as an instant variable. In the function, actually they don't have the initialization. So if you put integer I semicolon instead of initializing the I equals 0, then the compiler may complain. So initialization is something that you need to take care of. Some language don't have initialization facility. You need to assign it. Some language do have it all the time. Some language you need to look at whether it is supported somewhere or not. In Java's case, the instance variable is initialized, but the local variable in functional methods is not initialized. And aggregates actually is a compound multiple data field value. Compile time custom value of user-defined composite. We have these different language that has anonymous objects, and that is aggregates. Expression evaluation assignment. So actually There are several types of assignments. The basic assignment is equal to, and then we have this assignment operator, plus equal, minus equal, time equal, division equal, and modular equal, percentage sign equal. And usually I read this as increase by, and this I read it as decrease by. So let me let's look at the previous example. This one, a plus equals 1. I don't read it as plus equal, because for you to quickly grab the idea, I usually read this as a increased by 1. So you always remember this operator called increased by something. Then you know that this one is increased by something. And that is my own way of calling it. And if you have this statement, it's hard to remember. You have a equals a plus 1. It is not natural way of understanding it in mathematical thing. So this one, I always call it this as a increased by 1. Okay. And this one say I have a variable x and you have the post increment. So I have an x and then increment is after it. So I always use that. Get the x value and then increase. If I have plus plus and then x over here, is the post of is pre-increment. So you need to do increment up x. I will read it, increase, and then get x value. So that will be easier for you to remember how the operator actually works. Okay, so this one I read it as increased by. This one I call it decreased by. The star sign and then equal, I call it multiplied by. Slash equal, I call it divided by. And then percentage equal, I call it take modular by. Okay, so it's handy, avoid redundant word, perform side effect exactly once. The side effect is to plus and then assignment. And then this is called postfix formula. This is the decrement, post decrement, and also post increment, and it can also be used for pre-increment and pre-decrement. And side effects. Side effects often discussed in the context of functions. A side effect is some permanent state change. So you actually assign something without your notice, caused by execution of function. Some noticeable side effect of call other than the return value. So there are certain effects. In a more general sense, assignment statement provide the optimal example of side effect. So we know about this. They change the value of a variable. So that's those assignments. Side effects. Side effects are fundamental to the whole Neumann model of computing. And that just means like it's everywhere. And because the Neumann model is most successfully being implemented in some language like C or C family language, so it become very popular in Neumann model. In pure logical or functional or data flow language, there are no such thing because they are more mathematically modeled. And the Neumann machine actually more computer modeled. These languages are called single assignment language. So whatever you want to do assignment, you need to do it by a single assignment statement. And they don't take the side effect assignments. Expression evaluation side effect. Several languages outlaw the side effect for function. Easier to prove things about program, closer to mathematical intuition, easier to optimize, often easier to understand. But side effect can be nice. For example, the random number. Random number has side effect of updating the seed or doing something behind you, but you just don't know. Okay, but this one actually, some discussion with side effect. We will move on. Side effects are a particular problem if they affect the state used in other part of the expression in which function call appear. It's nice not to specify an order because it makes it easier to optimize. Fortran says it's okay to have side effect. They aren't allowed to change other part of the expression containing the function call. Unfortunately, compiler can check this completely, and most don't at all. So this discussion just talk about how side effect will take effect on the languages, and basically the rule of thumb is just try to understand the side effect of every statement in the language. And because the side effect actually is not well documented sometimes, so you actually have to check every language by itself. It's hard to have a summary right here. Now let's look at the control structure selection. Structured program is a programming paradigm aimed at improving the quality, and the development time of a computer by making extensive use of subroutine block structure for and while loop, in contrast to using simple text jump such as Goto statement, which can lead to spaghetti, causing difficult to both follow and maintain. Okay, this is actually very busy sentence. You know, it actually doesn't make you easy to understand what is structural programming. To be short, the structural programming is trying to make your program to have some structure. So instead of writing a long paragraph or long article, I would like to see some people write a report or article with section 1 such and such, and then section 1.1 such and such, section 1.2 such and such. Those kind of report is easier to read. And if you put the whole technical report in a whole article without labeling, without bullet items, without a numbered list, something like that, it will be more difficult to read. And you say that, okay, in the language, in the English article, you may have you need to refer to certain article, and it's hard to find. But if some people just say, okay, refer to page 25 and then section 2.5, something like that, it's easier for you to find something. So that's what structured programming is. So you had a sequential statement, you have condition, either true or false, you have repetition, and repetition have 4 types. You have for loop, you have while loop, you have do until, you have repeat until, you have do while, you have for each loop, you have several different loop body. And there is another not shown here, that is the procedure or function. These are all called the basic building block for structured programming. Structured control flow. Statement sequencing, you had a sequencing, of course. Selection with if then else statement and the switch statements. And iteration with for while loop statement. Subroutine call, you have function method call, all of which promote structural programming. I think that everybody knows this. Okay, that's not hard. Break level, you have pass, continue, break, return, exit 0. So this is what I would like to spend more time on. Okay, let me go back to the previous page. The break level for pass, continue, break, return an exit 0. The pass statement is just to pass certain function. So for example, I can have if x equals 0, then I pass, then I do nothing. This pass statement is available in Python language, but not in other language. In Java, if you just want to pass, probably just put the curly braces on the left and on the right, then do nothing. You will do nothing. So this one is statement passing. Continue, usually used for the for loop. You have or while loop. You finish in the middle of certain iteration. You put continue, then the iteration will be finished without finishing the whole iteration. You will jump to the next iteration. So continue is used to break one iteration. Then the break, if for example I have a while loop and in the middle I execute this break statement, then that break statement will be finished the whole loop. So break statement is to break a loop, and return is used to break a whole subroutine or function. And then exit 0, that is a system call. Sometimes it is system.exit parenthesis 0. That will break the whole program. So this is actually from lighter to heavier of different breaking level. For a single statement, for a iteration, break is for a loop, return for a function, exit 0 for a program. So this is breaking level of different program hierarchy. COBOL has the statements, compound statements, and then program structure or loop, procedure or function. These are different COBOLs. Now let's look at selection. The first topic, selection. Selection has condition switch, if else, if else. So basically you have if statement, case switch statement. These are the two major type. Okay, and in the if statement you have if then, else, and then some people or some language have this if then, else if, else structure. And some language like Ruby has this if then, else if then, else if then, and else statement, and it ends with one single end. Argo 60 is similar, but it doesn't have the else if. So you need to have if condition then, else if condition then, something like that. C has this switch, case switch. Same for Java. You have put the expression here, and then you put your value for that expression for a certain case. And remember, you need to put some break to finish. This break is used to finish this, actually to finish this whole switch statement. So switch is considered as a statement, and break will finish the whole statement. Otherwise, you will continue to the next one. Or if these two doesn't exist, you will go directly to body 1, body 2, body 3, and then break. So the break is actually breaking the whole loop or whole language structure. In this case, switch is considered a language structure. And that's the case switch. And in this usually has the first element in a list. So this is called a list. The first one usually is a operand, operators. So this one is condition. Condition 1, you do evaluation 1. Condition 2, you do this. So this is the way they do this case switch in this language. Selection. Fortran use the computed Goto statement, and sometimes some people use jump call for selection and logically control loop. No point in computing Boolean value into a register and test it. Instead of passing register containing Boolean out of expression as synthesized attribute, pass inherited attribute into expression indicates where to jump if true, and where to jump to if false. So actually this is not difficult. I will just go on next one. Selection jump is especially for in presence of short circuit. Okay, this is part we need to be careful. I mentioned about short circuit already, and actually right here, A and B, you will short circuit if A greater than B is false, then C and D will not be executed. And this or, if A and B and C and D are true, then this E not equal to F will not be executed. So those short circuit need to be careful. And right here, I will show you a assembly call that is to implement the Pascal language is this short circuiting. So right here, first we load A to register 1, and then we load B value to register 2. And then this expression right here is setting the register 1's value with R1 as A greater than B. And then we load C and load D and compare C and D here. And then we calculate the value for register 1 and register 2. The result of these two expression, we set it to R1. So R1 has the result up to this parenthesis. And then we load E and F. So E and F, we actually calculate it, and then we perform not equal, and then set in the whole expression to R2. Then we perform R1 mode R2, or R2, and then set it to R1. So R1 will be the result for this whole thing. So if R1 equals 0, go to L2. If R1, the whole thing is false, we go to L2. L2 is the else statement. If it is not equal to 0, then we go into the L1 part. It will be the then part, and then we go to the level 3. So this actually will implement this Pascal if selection statement. And now is the part that we generate a short circuit. To generate short circuit, we need to implement in this way. We load A, load B, and then if R1 is equal to R2, then we go to label 4. Label 4 actually is bypassing this C and D. C and D is in between here, and it would directly jump to label 4. That is to finish up this and then trying to OR with this E and F stuff. Okay, and if this one equal to R1 equals R2, then we go to label 2, then we actually go to else part. And actually this statement, actually this one, okay. And if this, if not equal, actually it go to into, not equal is actually this part, it will go into then statement and go to label 3, and so finish then and go get out. So actually, this is the way using the conditional statement to implement the short circuiting. And you just need to know where to bypass some code that you don't want to do. So apparently, you can see right here on the left hand side you have a high level language, and I'm sorry, on the left hand side you have a high level language. On the right hand side you have the arithmetical, and the discussion on here about this short circuiting implementation is when you write a compiler that you need to operate this left hand side high level language, then your action routine need to generate this code to implement that, so that you generate the right assembly code when you do the compilation. That's why we need to study this mechanism for selection and the short circuiting. It is helping you to develop the compiler to support the high-level language. Right here is a jump table. This jump table is used to implement this C language case switch statement. And it is a little bit busy, and let's get started, okay? So right here we have label T, and label T has a jump cable. And as you can see, these jump cable are the edges of several labels, okay? So this one is actually a edges of certain program that we call it L1 handler. So it's actually a L1 handler. So let's look at this. First, this is called the so-called control expression right here for C case switch statement. So first, we calculate a controlling statement and assign that value to R1. So we assign this value to R1, and if R1 less than 1, R1 less than 1, what does that mean? R1 less than 1, we have the case value, and right here we are trying value 1. If the value is less than 1, means what? Means it will directly jump to the default condition that will execute cross E. So right here, if it is less than 1, we have no case that will match it. Then we go to label 5. We go to label 5. And then execute the cross E, right? And then that is the default condition. And then if R1 greater than 10, we have case value 1 to 10, and it's greater than 10, we go to L5. That is also the default procedure for cross E, okay? Then if the value is something between 1 to 10, and we actually subtract the lower bound. So R1 is decreased by 1. So we have R1 equals 1, we decrease by 1, so R1 value becomes 0. Why 0? That is because we need to check the table with the index 0. Index 0 means this right location here. So this one we actually give you a array value of the T, and that's the offset value. So the offset value right now, if it is R1 equals 1, then you will get 0. R1 equals 2, you will get 2. And then you assign that value, table's value, say, for example, if right now R1 equals 1, I minus by 1, I get 0, then I come here. This TR1 will become edges of label 1, edges of label 1, I'm sorry, click the wrong thing. Edges of label 1 will be passed to the R1, and then we will go to body of the edges of label 1. That would be the label 1. So this actually means here you put the edges of label 1 assigned to R1, and R1's body, this sign I call it body, it actually go to the body of the edges of R1, label 1 that actually equal to go to label 1. So go to label 1, you will go to this clause A, and this clause A actually will execute this. So right here, if R1 equals 3, say, R1 equals 3, then R1 minus 1, R1 become 2. Then I find a table of the 2. Table offset 2, you go to here, you get the address of label 3, and you assign the address of label 3 to R1. And then we go to the body of the address of label 3. Actually, it's go to label 3. We will just jump to label 3 and execute this clause C. So, to be short, this whole assembly code thing is to implement this case switch in C language or Java language. So this is the jump table implementation of switch. Okay, before we continue, let me check if Miguel okay about the jump switch. I know this is a little bit busy for this thing. Okay, let's go back. Let me check how many lectures we have. Now we are at page 41. We have totally 60, so we still have 20 slices to go. Okay. So today we won't go too much over time. Probably will be able to finish within 2 hours at least. Okay. So loop, we have 4 types of loop. While loop, do while loop. Sometimes it also called repeat until. And in Python, they don't implement this. And we have 4 loops for each loop. And in reality, all of these 3 other loops can be implemented by while loop. So while loop is the basic loop. All of the other loop can be implemented by while loop. So while loop is the basic repetition. And for loop is while loop with initial condition and the update condition, update statement. So this one, you have the initial condition, you check the continue condition. If it is true, we continue. And then at the end, we update the loop index or some update condition and go back to evaluate again. That's for loop. While loop actually just check the condition. If it is false, we get out. Otherwise, we go into execute it. And this initialization or the statement actually is optional, not really needed. Repeat loop, we actually go into the loop directly, do something, and then check the condition. And for each loop actually is a special case for loop that actually access certain list or certain array to get some value from that composite data structure, and then directly get some element and then run the loop. Iteration, enumeration control to loop. Sometimes we call it index loop. So Fortran Pascal style for loop. And this, to implement the loop, actually you have these following different things to handle. You have the scope of the control variable. You have the change to bounds within loop, change to loop variable within loop, and loop after the loop, value after the loop. So these are a few issues we need to take care of. Can iterate over element of any well-defined set. And this is not difficult. Repeat a collection of statements a number of times, where in each iteration a loop index variable takes the next value of a set of value specified at the beginning of the loop. Okay, these are simple. I don't want to waste too much time here. So for loop, actually we have expression 1, expression 2, expression 3, And then we actually do this first. That's the initialization. We get in, and then each time we just check this expression 2 at the beginning, and then update. That's number 4. The update at the end of the for loop, and then we keep running it. And in case that you do not write anything for expression, you do not write anything for expression 2, you do not write anything for expression 3, this for loop will be exactly the same as while true, while loop with the true condition. So if you do not write anything, that this loop will become the while true loop. And if you don't write anything in expression 1 and expression 3, and you just put something in the middle for the Boolean condition, then that for loop equivalent to while loop. So for loop is actually quite a good loop. It can actually be downgraded back to while loop, and it can also be a so whatever while loop can do, actually for loop can do. And for loop has extra setup and then update condition. Of course, on the other hand, vice versa, if you have a while loop, it can also do everything for loop can do with proper setup on the initial condition and the update condition. For each loop, this is an example of for each loop. On the left-hand side, this is actually a pseudocode. It's not really any language like this. So we have a sequence of 18, 20, 32. We actually get every sequence element X from the sequence and then print it out. So we actually print out 18, 20, 32. And on the right-hand side, we have an algorithm. And this algorithm, we will sum the first n integer. So we input n, that's a number of integer. And then we actually assign sum to 0, that's initial condition. And every time we update, we add sum with the value I, and then output it. Here is the Python example. Remember this argument V1, that's actually in the program's interface for the argument string, that you actually get the program's first argument on the command line and then convert it to integer and assign to n value. This is not hard. Let's move on. Logic control loop. We have index control loop, and then we also have logic control loop. Logic control loop usually are talking about while loop or this while loop or the do while loop. And some language have the repeat until loop. Right here we put a P. P means Pascal style. And here we put C. C actually means C style. And we can also have this for loop, but this for loop actually make it through. And then in the middle, we insert a if statement with break. So break will break the whole loop. So this one actually is a mid-test loop. Using for loop, you can implement the mid-test loop. Usually we have the test at the beginning that is for loop or while loop, or you have the test at the end of the loop that is do while loop. But you actually can use the for loop or while loop and put some statement in the middle, can form a mid-test loop. So that is one example for that mid-test loop. Iterator, Python iterator for pre-order enumeration of the node of a binary tree. And CRU, Python, Ruby, or the C# allow any container abstraction to provide an iterator that enumerates its items. The iterator resembles a subroutine that is permitted to contain EO statements, each of which produces a loop index value. For loops are then designed to incorporate a call to the iterator. Okay, To be short, many languages, including Python and Java, they allow the iterator or iterable interface that actually a binary tree or any data structure that designed by programmer, and if that is not a linear data structure, you can always design a iterator so that the element in the binary tree, red bread tree, or you have different tree or graph, they all can have a iterable. You always have a iterator, so that data structure can have linear traversal. The purpose of having a linear traversal in a nonlinear data structure is if you rely on the linked list or the path that exists in a nonlinear search path. Sometimes if you just need to print out the data in the tree or in the graph, it doesn't need to visit every node in that graph or tree. For example, I want to print out all the data in those components. Then you will have difficulty to print it out because you need to evaluate the binary tree. And if I have the iterator, then I just need to use a while loop or for loop, continue to call the has next to check if there is one next available. Then I can always traverse through the whole tree without very difficult recursive code to evaluate each node. So let's look at this binary tree, bin tree. So the constructor actually set this left, right, child, and data to be none, to be null. And then we pre-order. So actually, for the tree element, we actually have pre-order. And then we set up the order by this yield and pre-order function to set up the order for the tree. So that actually provided the order. So let's look at this Java iterator. Iterator has three methods: next, has next, and the remove. So next is to access the data. Has next is to check whether there is a next variable or not. So let's look at bin tree in Java case. So this bin tree, binary tree, bin tree of the T data type is a generic. Implement the iterable interface with T data type. So we have left child and right child is value. And this iterator function, that is a method in the iterable function interface. And this iterator has created a tree iterator, and that is the implementation for this interface only method. And then this tree iterator implement iterator. Tree iterator implement iterator, and iterator has these three methods. So this one actually provides a step of such a tree type, and actually it uses the tree step to create an order. So this one actually the constructor it will push. If you have an unknown, and then you will, if it's not null, then we push that in. So we continue to push in, and then if we finish some subtree, then we pop, something like that. And if there is no element, we return empty. So the next one, if doesn't have next one, then we throw a no such element exception. Otherwise, we will get the value n node with its pop. And if it is not right, is not null, then we push write in. So actually, this one is a deep first search, but right first, right, because right push first, and then we push left next, and then if right and left being pushed, and actually you return the value at the end. So this is the deep first search order, and also right first, and then left, creating the order in tree traversal format, binary tree traversal format. Okay, let's look at this lecture 6, function and recursion. So we finished the selection and iteration. Now we go into the procedure and the function. And right here, for functions, we have these following issues. We have procedural abstraction. So use subroutine to encapsulate the collection of statement and subroutine code can be treated as a single statement. So that actually trying to reduce the repetition. That's one purpose. The other purpose is try to create some sort of abstraction so that you don't need to go into the detail for the procedure if you just call some other people's code. And then recursion is to provide a way that programmer can perform programming in different way of program. And concurrency, it will not be covered right here. It will not be covered in this chapter. It will be covered in chapter 13. But concurrency is implemented usually by coroutine. Coroutine means two routine that is executed either in true parallel or in pseudo parallel. So that's called concurrency. That's why concurrency is also part of the control structure. It said that it is running in parallel or pseudo parallel, and they are coroutines that are two or more subroutines that can run at the same time. So that's what concurrency is. Non-determinacy, actually the execution among alternative constructs is deliberately left unspecified, indicating that any alternative will lead to a correct answer. So right here, actually we have a basic procedure, recursive procedure, and then parallel procedure, and non-deterministic procedure. So these are 4 different types of procedures, and it all begins from these basic procedures. So we have subroutine, function, and the methods. Method usually is a term used for object, and that because the method is used for an object to modify the value or access a certain value. And function, in conceptually, is something input and something output is called function. And subroutine is actually we have a control flow, and then we jump to somewhere and then come back as a subroutine flow. But these actually had similar meaning in programming. Actually, even the name are different, but to me, it's all the same. It said that sometimes subroutine means no return value, but function usually means there are certain values, and method means, excuse me.
Call from 4758.
Method actually usually means that it's a part of a certain object. And we have this. Okay, let's move on. Right here is the method signature. And method signature including the name and the parameter list, and also the return value, the visibility, and the state or non-state, static or non-static. This is called the whole signature for a method or function. And usually signature is the identity of a function nowadays to check whether a function is the same or different. And here is the function's method body. Call stack. And call stack, we talk about this in where? We previously talked about the control flow for call stack in probably chapter 4 or chapter 3. Okay. So function, you will have call stack. So we have a main program. We go from line 50, statement 50 to 53. Then we jump to 89 and 80. Jump to 88 and 88 go to 89 and jump to 502. 502 go to 505 and go to 720. 720 go to 722. Go 780 and then finish 785 and then go back to 723. So this 723 is usually called the return address of subroutine 3. And then we scale to 725 and go to the return address 505. So the return address usually is stored in your call frame. So usually when we call 53, we push in the return address to the stack. And then we go to 80, jump from 89 to 502. So we set 90, push it into the stack. And then continuing to do that, we have all the return address over here. But usually the return address is part of the call stack. And we call this one record is one call stack. Exception handling. Exception handling is also some kind of a subroutine. But it's different. The difference between exception and the subroutine is exception actually has outgoing exception object. So when we write a exception, write a function, then we have to say, right here we have send request and throw IO exception. And it is not in the parameter list. It's outside. You need to write throws IO exception. To me, I call it a outgoing exception object. So usually you accept some parameter into the function. So you call and then say this right body, it create trouble, and then it got an exception. Then it throw the exception as outgoing exception, outgoing parameter, and outgoing exception being escalated to its parent and still have no handling routine. It will be escalated to its grandparent, and then right here, the capture statement will accept that IO exception object as a parameter. So this catch statement is just like a function that having the parameter, and then do the following thing to handle the error. So this catch statement, the object is IO exception E is just like an incoming exception object as parameter. And for this send request function which throws IO exception, that can be considered as a outgoing exception object. So exceptions are handled just like procedure. You can have the outgoing parameter or incoming parameter and have the try catch block. And also, you can put the outgoing exception object into a function declaration. So basically, it goes through 4 steps. When exception occur, you have problem occur, and then you create an exception object as an outgoing object, and then that outgoing object will be escalated to a certain level that handle this exception object. We call it the exception handler, written in the higher level of the program. Recursion. Recursion is equally powerful to iteration, and actually it was proven that anything can be written in iteration can be done by some recursive program, and vice versa. Any recursive program can be converted to iteration. and then iterative program. Sorry. And then there is a mechanical transform back and forth, and more intuitive for recursive case, naive implementation less efficient, and it actually takes more time because you have the push and pop of the call frame, and sometimes also get the context switch in process involved. So it's fundamental to functional language like Scheme. Let me check how many pages we have. We are 56, so we have 4 more pages. Recursion subroutine that call themselves directly or indirectly. So some function or some subroutine call themselves directly or indirectly is called the recursion. And sometimes you call themselves or you call some other function, and some foreign function also call you. That is indirect recursive. That is also considered as a recursive, but it's called mutual recursive. Typically used to solve a problem that is defined in terms of simpler version. For example, compute the length of a list, remove the first element, calculate the length of the remaining list n, and return n plus 1. And every recursion needs a termination condition. For example, if the list is empty, then we return 0. Without termination condition, usually the recursion will go into infinite recursive call, and then the heap will usually be and call frame will and heap will usually be out of overflowed, and then create a system crash or exception. Iteration and recursion are equally powerful in theory. Iteration can be explained by recursion and vice versa. Recursion is more elegant to solve a problem that is naturally recursive defined, such as tree traversal. Recursion can be less efficient, but most compilers for functional language are often able to replace it with iteration. I personally prefer the iterative programming instead of recursion, but I can also write good recursive program. Right here, let's look at the tail recursion. Tail recursion means no more computation following the recursive call. So right here, we have one example. We have GCD, and we write if 2 are equal, we return A. Otherwise, if A greater than B, we return GCD of this. We actually have the minus sign and the B. Actually, you can also use B and actually, I'm sorry. Actually, you can put the B here and put A take modulo by B. That's also working for GCD, but right here is using the subtraction method anyway. But once you return this, there's nothing you need to do. That we call it tail recursion. So right here, it's a tail recursion case. So comparing these two functions, if you have a function that calls itself, and after it returns for the lower level recursive call, then this is called tail recursive. But on the right-hand side, the one that you actually need to do something more, that is called not a tail recursive function. So in addition, you can do more for tail recursion optimization. The compiler replaces tail recursive call by jump to the beginning of the function. Tail recursion optimization, and actually this shows you how to consider the following GCD function. A good compiler will optimize the code into this, and actually this one can be optimized, can be converted into iterative function like this. And as I mentioned, You don't need to use the minus or subtraction algorithm. If you use the modular, you put B here and A modular B, that actually will be faster than this version. But right here, as you can see, the compiler version, they don't actually use the recursive call. They've been optimized into the Goto statement, or you can even write this. So actually, recursive usually is provide a theoretical beauty, but actually in real compilation or real world, it's not that practical to use. When recursion is inefficient, Fibonacci number is one example that it takes exponential time to compute. So how can we very easily identify some recursion is ineffective? Usually the second degree is not effective, not efficient, because any of the second degree recursive program, the order of the peak O rotation will be 2 to the order n. That actually is the recursive function will grow too fast. It is not checkable. And usually only the linear recursive, like one function call another smaller case, that kind of recursion is actually efficient, and not for this kind of the second degree recursion, or even not to mention third degree or fourth degrees of recursion. Usually anything that starting from second degree recursion is not practical in real world applications. Okay, I finished this week's talk. It's probably the shortest so far, and actually simplest as well. Let me check if still any question. Otherwise, I'll call it for the day. Okay, then we will finish here, and hope everybody enjoy the weekend. Okay, bye-bye.